All right, well, welcome everyone. It's 3:30, so we'll go ahead and get started. On behalf of EOL, I'm pleased to introduce Dr. Peter May for today's EOL seminar. Dr. May received his doctorate from the University of Adelaide, Australia, with a focus on VHF radar studies of the troposphere. Dr. May led the Bureau of Meteorology's research program from 2009 to 2020, which has afforded him key roles in major national initiatives, including the world-class meteorological research capability of the RV Investigator, the development of the Access National Research Initiative, the Australian Antarctic Science Partnership, as well as international partnerships such as the Unified Model Development led by the UK Met Office. Dr. May also co-led the largest meteorological field program in Australia, involving more than 100 scientists from more than 10 countries, including 6 research aircraft and Australia's national research vessel. With more than 130 peer-reviewed publications, Peter's research interests are focused on radar meteorology, using wind profiler radar and polarimetric radar to study cloud systems for both weather and climate applications. This has included a wide range of activities from basic signal processing to methodologies for the retrieval of cloud microphysics and the application of these techniques to the study of convective dynamics, the impact of convective clouds on the environment, and cloud processes over the Southern Ocean. Please join me in welcoming Dr. May for his seminar on ocean-going dual pol radar.
Thank you. So there's a long list of people I should acknowledge here. So the way this talk's going to work is I'm going to talk a little bit from a book chapter that I wrote with Valentin and Alain and Brenda and Masaki and so forth as part of the book on advances in radar that was edited by Bringy and Mahala. I'm going to follow that with some work with primarily, there's a few highlights from work done by some of the students, Larry and Steffi and Sunny, and their main supervisors, Huang and Steve Siems. And then I'm going to finish it off with a bit of work that's currently in progress and just making use of the investigator. So I'm going to start with a little bit of history. So this is from chapter 8 of the book. And now, I learned a lot when we were doing the research and development for this book, and one of the things Masaki really taught me was how much work had gone on in Japan that we just didn't realise. I certainly hadn't realised. So the first weather radar on a research vessel was actually on 2 research ships in Japan in the 1960s, early 1960s. And the radar data was recorded either by photographs or people drawing sketches of what they saw on the screen. There's quite a lot of literature. A lot of it is in Japanese, but I think we should acknowledge just how far ahead they were. Now we think of the first stabilised radars that we think about was actually during the Gate experiment, the first time that many radars were coordinated. Gate, of course, was just enormous of the scale that we can't comprehend these days with multiple ships, a huge number of aircraft, and it was really seminal for our understanding of tropical convection. Some of the Gate cases are still used for validation for cloud resolving models to this day. And the picture on the top left there, the conceptual model of HOWS is something that isn't out of place in a textbook today. I would point out, though, that that's okay for a score line. There's an awful lot of tropical convection that looks very different to that. But nevertheless, this was a seminal experiment. It was also one of the first times, at least for ocean-going radar, the data was digitally recorded. So a major undertaking. The first big Doppler radar experiments was Toga Core. There's an example there from Walt Peterson as part of his PhD work way back doing dual Doppler analyses of some of the core score lines. And since then, of course, there's been many, many more experiments. On the theme of Japanese innovation, I would also mention one of the things that happened between Gate and Core was we started stabilising the radar antennas using the antenna beam control to control the elevation while the ship was moving underneath it. Jeff Keeler did a lot of work here at NCAR on developing that. The Japanese beat NCAR to the punch by about five or 6 years. They were doing it on the Japanese radars before then. So there's stuff there which we've never heard about. So if we move along to the 2010s, we've joined the dual polarization era. We designed the RV Investigator from scratch beginning around 2010. I'll talk a little bit more about that in just a moment. The radar on the Mirai was upgraded to Dual Pol in, I think it was 2017, and the C-Pol radar that CSU developed, which has been used on a variety of US ships, was also developed. These are all C-band radars with beam widths of around 1.3 degrees. There was still there was a failed execution, but a planned X-band radar to go on Australia's new icebreaker. And the Taiwanese are planning on putting a radar actually very similar to the Investigator radar on their new research vessel. That's tied up with some spare parts and stabilisation apparently, but it's not far away that they'll join that relatively small club. So a little bit about the RV Investigator. So Australia's a relatively small country, at least in population. So we have a research vessel. It's Australia's dedicated. It's around 94 metres long. It's not a small ship. It has an endurance at sea of around 60 days. It was launched in 2014. It had a radar design, radar on board from day one, but it took a couple of years with the manufacturers before we started getting good data out of it. So it's basically data from about 2017. This is a multi-purpose vessel, so it's designed with geophysics, fisheries applications, biological applications, physical oceanography, as well as meteorological research. So it's our national facility, and a little bit like NCAR facilities, you have to propose. If your proposals, it's a competitive process, and if your proposals are accepted, you get that ship time. You're not paying the $60,000, $70,000 a day it takes to operate the ship. I had the pleasure of being involved in the design of that vessel, working with my geology colleagues and fisheries colleagues and so forth. It was, none of us got everything that we wanted, but it was personally it was a highlight of my career because it was just this collegial atmosphere where we worked together to create the best capability for our nation. The ship is extremely flexible. You can deploy containerised laboratories on it. And I'll talk about the potential later in the talk. I'll talk about some of the sampling. But the core instruments operate on every voyage. It doesn't matter what the purpose of that voyage is. So we have, by now we have a very large number of voyages that include dual polarisation radar, optical disdrometer data. We designed it with at the front of the ship. There's inlets for aerosol and greenhouse gas measurements, so it's basically a mobile global atmospheric watch site. And we measure bulk fluxes, and that's about to be upgraded to sonics. So it's a very capable ship with a long pedigree. A couple of things about operating a radar on a ship. Calibration is a much harder issue than it is by land. You can't use targeted spheres and so forth. So what we do for reflectivity is we use the GPM radar as a standard candle. That can be an issue, particularly in the Southern Ocean, where the quality control of GPM actually throws out way too much data. And the other calibrations that we use, apart from solar cals, is we take measurements of comparisons of opportunities with the ground-based operational radar network along the coast. The next question is, how do you calibrate the ZDR? You can't point the antenna vertically because the ship moves and the software is such that there's potential instability. So the maximum elevation that we can raise the antenna to is around 75 degrees. So what we've done in Australia is we've taken the same approach as for the Mirai radar, where we look at very weak echoes low down to the surface. Should be the order of 0.1 of a dB, and use the offsets. This example on the middle plot here, you can see when, as a quality control measure, you can see, guess when the low noise amplifier broke. So, real-time quality control. And the other way we do this is we look at relatively low reflectivity echoes from snow between around -5 to -15 degrees. Look at the PDFs of the echoes, and again, the offsets should, the population value should be around 0.1 dB, so we can use that. We've found that is pretty stable, but we still do it on we separately calibrate every voyage, because there's the odd times people tinker with the radar without actually telling us, so it can jump. Sea clutter is an issue. So the radars are very good at measuring the echoes of little waves in the ocean. At X-band, they're capillary waves. At C-band and higher, it's actually gravity waves. This is echoes off a surface. And so whereas the power returned from volume scatter goes down as 1 on R squared, this is because the volume of the radar pulse is increasing with range. Here you've just got a surface, so relative to volume scatter, the power drops off as 1 on R, and you can see that drop off here in the sea clutter. You can see that our antenna's probably not precisely flat, just with the anisotropy there. And you can see a smaller anisotropy in the differential reflectivity. Interestingly, with these these small waves, the Doppler shift of the waves actually seems to pretty accurately match the low-level winds. And so you can see wind shifts. You can see this in our coastal radars in Australia as well, that with wind changes coming up the coast. It's not completely clear to me how long the response time is, so there's a potential delay there, but you do see potentially useful information. And this panel here just shows the return power, what we see compared with what you'd expect for volume scatter. And typically the differential reflectivities are quite large negative ZDRs. So you can discriminate between them, but they do definitely has the potential to contaminate rain estimates close to the vessel. The last thing another additional thing that we started to think about was what's the effect of the ship motion, where the ship is rolling and pitching, and we're stabilising the antenna. But if you think about it, if you think the ship is rotating or rolling, but you're keeping the antenna pointing at the same direction, what that means is the angle of the polarisation is no longer vertical and horizontal. It's tilted with the ship movement. So you can model some work we did with Mahala Tarai many years, more than a decade ago now. We actually treated that as a mean canting angle, and Mahala did T-matrix calculations to look at what corrections, if you needed to make corrections. And the shorter answer is, for typical ship motion, which is a roll of less than 5 degrees, it's kind of not worth doing. If you're in extreme conditions, then it's probably, you need to start thinking about it. If your ship gets to 45 degrees and you've lost all your polarimetric information, that's the least of your worries. So, Valentin is processing all of the data from all of these voyages. So there's a long list of QC processes. to produce data sets that are available to the community. I'll touch on that at the end. So he de-aliases the data, applies various masks and filters, corrects the ZDR for noise following the similar methods to what NSSL developed, attenuation corrections, all the usual thing. For the gridding, the original version of the data just used a Barnes analysis. I don't know why they used a Barnes analysis, but that's what they did. The latest version, which is just in the process of being generated, we're actually taking a 3D VAR approach to the gridding of the data, which is a lot of... And then there's downstream products. We've got QPE, rainfall estimation. We're estimating ice content using the methodologies that Alexander Ryzhkov and the Canadians have developed. We've got DSD parameterizations, and we're applying Brenda Dolan's hydrometeor classification. We'll probably improve on that sometime in the future, but for the moment, we're doing the fuzzy logic thing. So for every volume that's collected over all of these voyages, for all of the years, we have all these fields. So this is really just a slide to say, this is what we're doing, and this is what's available. Okay, so let's move on to a little bit of science that we've been doing. So the next little section we're going to do is we're going to focus on the Southern Ocean. So many of our voyages and most of our dedicated, all but one of our dedicated meteorological voyages have been into the deep Southern Ocean. And apart from being a cool place to go, the reasons that you want to do this is in our weather and climate, particularly in our climate models, there's major discrepancies in top of atmosphere radiation. Over the ocean, there's very large differences between the various precipitation data sets, be they reanalysis or satellite products. There's a huge range and in the CMIP, in CMIP 6, a large chunk of the changes in climate sensitivity were actually traced down to the radiative impacts of clouds in the Southern Ocean. So I'm not going to touch on all of that, but there's students have worked on a few elements that I just want to give you a flavour of. So the first little bit is student Larry has just literally submitted his PhD a couple of weeks ago. The first part of his PhD work, which has been published in JGR, he was posing the question, what precipitation characteristics do we see in the radar data and disdrometer data on the vessel? And our initial estimations of rainfall estimations that Valentin and Alain were using were based on the Thompson algorithms that were developed for the tropics that the CSU group were using. So I'll come to how some of the changes in that. So a couple of things. The Southern Ocean is actually a really rainy place. It's rainy and it's cloudy, but a lot of that rain is really light. So the disdrometer actually sees a lot more than what we see with the radar. The minimum sensitivity of this radar at 50 kilometres is at 100 kilometres is around 10 dBz. It's not the most sensitive radar. I was a little bit of disappointment. But just to give you a little bit of an example, here's just a sample. Let me take you through this. So this is an image from the Himawari satellite, just showing the cloud field. This little ellipse, because we've squared, is the radar coverage. The blue dots mark where an objective thing has found cold fronts. You've got warm fronts. And this is just a sequence of measurements at the vessel where the rainfall measurements are actually measured from the disdrometer. And so just to show a couple of examples, the sort of thing. So this is one of the lower tilts of the reflectivity as this frontal system was approaching. Horizontal transects, you can see the precipitation. There's plenty of bright band. It's all stratiform rain, large areas. Interesting structure in the differential reflectivity as you get go to some reasonably small values towards the tail end. So if we break that down a little bit, what Larry has done is he's used soundings from the vessels and looking at the profiles of low-level winds and some thermodynamic variables, done a cluster analysis of those to define some different synoptic regimes, which actually seem pretty robust across various places in the ocean. We've done similar things on the Tasmanian coast, on Macquarie Island at 55 South and so forth, and looked at which of these regimes are precipitating. Which is the one that stands out that surprised me is this M4 regime, which is basically the warm front. And the warm fronts in the Southern Ocean produce an enormous amount of rainfall, more than the cold fronts, which is personally I found very surprising. There's a couple of high latitude classifications here where you see quite a bit of snow rather than rainfall. This cold air behind the lows, you also see quite a significant amount of precipitation, and that will become important in a little bit when we look at how well some of the reanalyses and the satellite programs do. So this is really just some highlights of Larry's work. He's calculated the equivalent of CFAS, but using the temperature as your vertical coordinate for reflectivity and differential reflectivity for these different classifications. So around the cold front, behind the low, and in the warm frontal regime. And again, you see very strong evidence of bright band just around the 0 degree contour, kind of as you'd expect, but it's not very convective, even though some of the reflectivities are quite spotty, but it's dominated by stratiform rain. And behind the low and in the cold front, you can see the fraction of the area that is covered by rainfall echoes is just, on average, it's just a few percent getting up to about 10%, quite scattered, whereas in the warm front, significantly more area of precipitation. Larry also looked at from the disdrometer data, looked at the drop size distributions using both a normalised gamma distribution and a what he called the Delano distribution, which basically had a couple of variations of the shape parameter. And surprise, surprise, if you have more things to fit, you can get a better fit. But looked at coming out of that, one of the things that he looked at was if you estimate the rainfall from the disdrometer data and from the rainfall rate from the disdrometer, and you put the raindrop size distributions into scattering calculation, you actually get remarkably good agreement. So he then went to do some tuning on the rainfall estimators. I won't go into the gory details here, but suffice to say there's actually some pretty tuning those fits actually were quite different coefficients in the rainfall estimates. And if you look at a scatter plot between the observed rainfall rate versus what you'd estimate from the various radar parameters, with these different colour-coded, depending on the range of the KDP, ZDR and so forth, you can see there's quite a bit of scatter, almost using these tropical relationships, and if you tune it, you get a much cleaner relationship. So we're actually applying those cleaner relationships now in the Southern Ocean for the version 2 of the data set. So a few of Larry's conclusions in that paper. From the disdrometer, it was just the precipitation. It was drizzle and light rain a lot of the time. As I said, the radars really doesn't, the dual pol radar, C-band radar, doesn't pick that up all that much. You certainly see it in the W-band radar data though. I think I've covered most of the rest of that. I'll just move on. So people that want more details, it is in JGR in 2024. So the next thing I want to look at is questions that we start. Now, using these analyses, widely, the iMerge project, which combines the GPM with infrared and other sensors, is widely used. And the iMerge people will say, well, haven't really optimised it for the Southern Ocean. But if you look at not just iMerge, and ERA, of course, is extremely widely used. If you look at these various satellite estimates and various reanalysis, the amount of rainfall as a function of latitude varies a lot. And so the question is, well, how good are they really? Can we use the radar data to do some evaluation and really show up quantitatively how well these reanalyses and the satellites work? So here's a couple of examples from different times. This is from Montoya, Duque et al. So the left-hand side panel here is the northern-ish part of the Southern Ocean, then further and much further south, down below 55 south. The first row, you've got Himawari data with some of these fronts analysed, and it's just a sequence left to right. And these little ellipses, again, are the area covered by the investigator radar. We'll zoom in the lower panel. So this is what ERA thinks that the precipitation is. This row is what iMerge thinks it is, quite different. If we zoom in where we've got radar data, and you think, no, we've got a little bit, this first time we've got a little bit of rain to the north, iMerge actually catches that okay. ERA has it in the wrong place. In the midst of this warm front where we've got very large areas of precipitation, they kind of look plausible. Then you've got this, this rain band going through. And again, they kind of both look plausible, but maybe they've got the magnitude wrong, particularly ERA is looking a bit light. You can continue the same thing at higher latitudes. ERA's got something here associated with, it's well behind the low. You've got, it's relatively unstable. You get these shallow convection. In this case, iMerge has got a few spots. Ocean Pole's seeing plenty. But again, there's pretty systematic and pretty serious differences. If we look at a time series of a particular event, the top panel, we've got the precipitation rate as a function of time and these various estimates from the radar, the disdrometer. This is ODM 470, iMerge and ERA, and you can see just from this time series, there's lots of variations across this. If you look at the accumulations, this next panel, you can see overall the radar and the ODM agree to a surprisingly good extent. You're pretty satisfied with that. ERA thinks it's rained quite a bit more, and iMerge thinks it's rained even more. So the next step that Steffi did to try and quantify this performance, she looked at the fractional skills score. I'm sure there's lots of people in the audience that are familiar with the fractional skills score, but it's there for reference for if people want to look at it later. So here are the fractional skills scores as a function of the spatial scale of the precipitation at different precipitation rates. So if you look at the ERA on the left, you see at low precipitation rates, there's terrible agreement. Basically, ERA thinks there's light rain all the time, and the radar is just not seeing it. But as you go up in rainfall rate, if you've got a bit of spatial averaging, it's not too bad. And when you get to the higher rainfall rates and in the deep Southern Ocean, 2 or 3 millimetres per hour is actually a pretty good rain rate. You think this doesn't matter? No. Who gets excited about 2 or 3 millimetres of rain until you work out the water flux associated with this and what it means to how fresh the Southern Ocean is, which in turn impacts the overturning circulation, da-da-da-da-da. It's actually a lot. You look at iMerge, and it actually does a better job with the light rain, but generally speaking, the skill scores are worse, and you've got to average over larger scales before you get something that's reliable. These hashed areas is where that fractional skill scores indicates that you shouldn't use the data. So there's a pretty narrow band and a fair bit of averaging you have to do before. So to summarise this, the area generally overestimates the precipitation frequency, and overall it gets the total accumulations about right. Because it's got lots of light rain, but it misses some of the heavy rain. iMerge has the opposite problem. It actually overdoes the heavy rain when you compare it under those post-frontal conditions where you've got these large areas of shallow convection, these mesoscale convective organisation and marine stratus with embedded convection. iMerge significantly underestimates the precipitation frequency. So the bottom line of this is, in the Southern Ocean, treat the reanalyses and treat the satellite products with great scepticism. Be really careful. This is really just quantifying what's a reasonably well-known bias, the drizzle problem in the reanalysis, but it is actually pretty significant. Just to throw it up there, Sonny Truong, as part of his work, has, amongst other things, also looked at a case study. He was comparing the observations with WRF with a couple of control runs, varying some of the microphysical parameters and so forth. So again, I can refer you to the paper, but I don't want to keep people here too long. So I just want to finish this off by talking about some of the more recent stuff, literally what we're doing right at the moment between Valentin, Louf and myself. And we're asking the question, well, we've got multiple years of data. This plot here on the right is where the ship has been over the last 5 years. Right from the deep tropics down to the ice edge. And we're asking, well, what are the latitudinal variations of the drop size distributions that we retrieve from the vessel? This is really we're just starting this, so there's a lot of stuff still to go. And this is important for satellite retrievals. It's important for a whole range of reasons. I'll show the next panel. I'll show there is potential for seasonal biases in this analysis. But I'll make the point we're just using the standard products that have been generated that are available to the whole community. For example, in terms of seasonal biases of the sampling, the geophysical people and the fisheries people don't like going into the tropics in the tropical cyclone season. What a bunch of wimps! But we have no data at the height of the monsoon yet. Conversely, all these people going into the deep Southern Ocean don't want to go in the middle of winter. Again, I can't understand why. What's an iceberg between friends? Just to sort of quantify this, each of these ticks is when there was a voyage over the last 4 years in each particular month at different latitude bands, and it's 2.5 degree increments on the latitude band. So, we're missing the monsoon. We're missing the high latitude winter storms, but nevertheless we've got a decent enough sample. For the drop size distribution, I'll just expand on this a little bit, in part because to give you some confidence, and in part I showed this at a recent talk where we were in a conference session that was honouring the contributions of Briggy, who's passed away. And this is some work that Briggy and Mahala and Chris Williams and I did back in 2009, but it's still being used by the Japanese and it's still being used by us and I think many other people. So we took a whole pile of disdrometer data from Darwin. Mahala did T-matrix calculations and regressions to calculate equations for the medium volume diameter of the rain drop size distribution and the number concentrations based on that. And in this paper, we then compared, this was in Darwin, and we had dual frequency wind profiling radars, and we could directly measure the vertical velocity with one. We can measure from that, we could then correct for the vertical motion, directly measure the fall speed spectra of the hydrometeors and calculate the actual raindrop distributions from the profiler data. So this panel here on the left is the reflectivity as a score line went through. And these panels on the right, the continuous sequence solid line is the profiler data. And as part of our routine cycle, every 10 minutes, we would do an RHI scan over the profiler site with the C-Pol radar. So each of those dots corresponds to the reflectivity a kilometre above the ground from this RHI scan. And you look at that, and that's an astonishing degree of agreement. And then the next frame down is the D noughts that we were estimating, and then the rainfall rates. And so I'm still astonished by that level of agreement. So that's the basis of what I'm going to show in the next few slides. So this is an example actually from the book chapter. There's a frontal rain band going through. There's a Bureau operational synoptic analysis here. This red dot is where we were, southwest of Tasmania. And you can see this nice frontal rain band, lots of embedded areas of higher reflectivity, pretty much dominated by warm rain processes. The reflectivity dropped off like a stone above the freezing level. That middle line is the freezing level. With the texture and so forth, we calculated the overall area of precipitation, the convective area, and is here in red. What area corresponded to convective rainfall, and a sequence of the PDF of the rain drop size distributions. So just again, show we can do this. Things look plausible. So the next thing we've done with the current set of data, and this is much more recent data, 2024. This is just a sample off the coast of the New South Wales coast. So the top panel is the reflectivity. It's used this 3D, this variational analysis to get the reflectivity at a 1 kilometre CAPI. This is the corresponding differential reflectivity. The rho HV is pretty high. This is the spatial distribution of D naught at a kilometre. And this right-hand panel is just taking all of that data for just that one case and plotting a histogram of the D naught along the x-axis, the log base 10 of the number concentration here on the right. And you see this nice descending slope, which is the kind of things that you'd expect, the kinds of number concentrations that you'd expect. If we look at another case at a higher latitude, this case 55 degrees south, and this is during a relatively narrow rain band. You can see a similar distribution. It's a bit steeper than the previous one. There's fewer small drops. There's a lower number concentration, and we just asked the question. Okay, that was fun. Is that a general result? So here's a couple of examples where instead of just taking a sample, we've taken every cruise, or every voyage, I should say. The marine people don't like saying cruises. They think it means it's a jolly. They want voyages. We're going to discover. Yeah. So here's three different latitude bands, 10 to 12 degrees, 30 to 32, and into the higher latitudes, 50 to 52. Similar distributions to what I've just shown, but it's every sample averaged together where the area of rainfall was greater than, I think it was 3 or 4%. I can't remember the exact number. And the average value, if you've got very good eyesight, you can see there's a little cross there. And these horizontal bars mark the 25 to 75 percentile range of those distributions. So you can see here, scatter plots of the D naught versus the number concentration again, the reflectivity versus the drop size. So higher reflectivity is bigger drops, no surprise, except as you go to these high latitudes, you're not getting very high reflectivities at all. But as I'll show in a moment, you're actually seeing pretty big drops. Likewise, the Z versus ZDR, higher reflectivities, higher ZDR, as you'd expect. And similarly, and if you look carefully, you can actually see there's a tendency here to steeper and steeper slopes of that D naught versus log N of W. So there is a significant trend there. There you go. I forgot it was 2%. I'm getting old. So if we take all of those, this is the second to last slide. If you look at the D naught as a function of latitude, this panel here on the left, and bear in mind we are not sampling the monsoon here, and we're not sampling the high latitudes in the wintertime. You see, it's pretty constant at a value of around 1 millimetre, and then once you get south of about 40 degrees, there's this gradual increase. And we haven't done deep analysis on this yet, but you start thinking about, okay, where's the freezing level? And as the freezing level is getting lower and lower, you start thinking, well, there's less chance for drop breakup as the snow melts. It's kind of plausible that even though the reflectivities and the number concentrations are going down, but the particle size is going up. You see kind of a step change in that D naught slope as well. Significant variations in the average reflectivities and that increase in differential reflectivity corresponding to the increasing drops. So as you get into the high latitudes, it's lower and lower reflectivities at these wavelengths. And bear in mind, we're missing all that drizzle with this radar. So a few things just to finish off. So we've got a quality controlled data set from ocean rain across many years. We're following the FAIR principles. It's findable, it's accessible, it's interpretable, it's readable. And that's been published at the Australian National Computing Infrastructure. That's another national facility along with the Marine National Facility in Australia. The version 2, which is what I've been showing those scatter plots of, is coming. It's a short way away. So it is available to the community. If you want to look at Southern Ocean precipitation, you're most welcome. There's more data than we can possibly look at. We've looked at, as a starting point over the last couple of years, we've started looking at the Southern Ocean precipitation characteristics and tuned some of the rainfall algorithms. We've looked at some of the commonly used products, both for reanalysis and satellite products, and they show we've got a long way to go in this part of the world. And in fairness, the satellite guys are really interested in this, as are the reanalysis people. There's clear latitudinal dependencies, so this is right at the start of this process. We haven't looked at, for example, how echo top height changes systematically, the relative contributions to convective and stratiform rain. There's a lot of stuff that we have to do. And I haven't mentioned other work. So, for example, Jay Mace has done some really nice work for quantitative snow and ice retrievals that I highly recommend. And just the acknowledgements that the Ocean Pol is supported as a marine national facility in Australia, and all this data supply and so forth is again part of our national research infrastructure. And with that, I'll take some questions.
Thanks, Peter. Very comprehensive. Quick reminder for those online, you can enter your questions in Slido. What questions do we have in the room?
Go for it.
Very nice talk. You mentioned that you also measured aerosols during your cruise, and in I think your second to last slides you showed differences in the cloud, like the distributions.
Yeah.
Is there a correlation with changes in the aerosol amount?
We haven't looked at that with the radar, with the investigator data yet. what we have, well, one of a different student, we have looked at this in the context of data measured from Cape Grim, where there's a very detailed aerosol record. And it's actually, the implications of Nassim's work is the aerosol content is dominated by how much is washed out rather than sources. And she's been looking at open and closed MCCs in the... So short answer is there's a question of the aerosol tail is not wagging the dog, or it doesn't seem to be. But it is important. And yeah, it's one of the things we will do as we start doing further analysis on this.
Thanks.
And you talked about salinity and the rainfall volume in the Southern Ocean. Is there a lot of moisture transport from the tropics down into the Southern Ocean?
Yes, is the short answer. Yeah, it's a separate talk. There's a paper in review at the moment from one of our other students, Xiao Yang, who's looked at rainfall records at Macquarie Island, which is basically the only spot in the entire Southern Ocean where you've got a long-term record for what's that's worth. And what he has done is, well, one step back. Steve Siems a few years ago looked at the observed trend of rainfall at Macquarie Island, and there's people who've looked at potential orographic impact and argued that it's not significant there. It's where the rain gauge measurements are is literally at sea level. And in that observational record, there's been like a 30% increase in the precipitation from quite a lot to a real lot. And it's like 1.2 metres of rain a year or something on this. In the reanalysis, the trend is a third of that. And so one of the things that Xiao Yang has done in this paper in review is look at what synoptic regimes, how the synoptic regimes have changed with climate change over 40 years, with the south expansion of the subtropical ridge. It actually has changed some of the mean meteorology there. That doesn't explain that trend. The only thing what is different is there's in the observations pretty much across the board in the various synoptic regimes, where it's frontal or it's post-frontal and so forth, we've seen dramatic increases in rainfall intensity. And in the reanalysis has none in the post-frontal stuff and way underestimates the changes. And if that difference between the observed and the observed shift in rainfall at Macquarie Island compared with what's in the models, if that's replicated across the Southern Ocean, that's a big if, but it is the only data point we have, that corresponds to a freshwater flux 10 times a missing freshwater flux 10 times what the ice melt has been.
And that change has been over, did you say 30, 40 years?
Yeah. But that's a lot in a relatively short space of time.
Thanks, Mike. So we have a question online from Matthias Steiner. It says, thanks, Peter, for a great overview of these oceanic observations. Can you elaborate on whether the observational insights gained so far confirm the understanding of our climate system and our ability to model it, or introduce new questions about things we don't really understand?
Well, I think we just touched on it a little bit just then. So I don't think we certainly don't understand the origins of all the origins of this trend. In terms of our confidence of precipitation, a significant amount of precipitation comes from these open and closed MCCs behind the low pressure systems and the cold air outbreaks. And that is not captured pretty much at all in either our weather or our climate models. It's really underestimated. So I think all this data is pointing to some pretty significant gaps.
Great.
Hi, thank you for a really great talk. We don't really get a lot of ocean ocean talks at NCAR. You showed a really interesting slide of where times of the year where the ship was taking measurements, and there were two kind of dead zones of observations. Can you explain why the dead zones of observations exist? Is it if it's weather or if it's the lack of opportunity opportunity?
Yeah, so this is a ship that's used for multiple purposes. So it's used for fisheries research, it's used for looking at the ocean surface, it's used, and the non-meteorological people, generally speaking, want to avoid tropical cyclones. So therefore, they don't want to be in the deep tropics off the coast of Queensland or off the Western Australian coast during the summer. So that's the tropical dead zone, basically. We're actually talking about proposing a cruise to focus in the vicinity of the Great Barrier Reef, where it's interesting for a lot of other reasons, not least the future of our coral reefs, which is dire. Focused in that January-February reason, but regardless, the ship would flee a tropical cyclone. It doesn't want to be around a TC, but the monsoon is certainly a target. Conversely, there's just a lot of reluctance to go to very high latitudes in the wintertime, simply because of the risk, the risks associated with that, with icebergs and severe weather, and just the difficulty of search and rescue. Search and rescue at that time of year at very high latitudes, it's always hard because you're extremely, you look at that map and think about how far from Hobart or Perth you actually are. It takes days, it takes many days of constant steaming to get down there. And search and rescue is very hard and if people get sick, for example, on the ship. So search and rescue is really hard in the warm season in the deep Southern Ocean, and it's nigh on impossible in the middle of winter. So just for that safety reasons, they don't go.
Autonomous it is.
As I said, wimps.
Any other questions in the room?
So one follow-up, Peter, then. The difference between the northern hemisphere and the southern, say in terms of the moisture, do you have a sense of that, like because of the different geometries of the oceans?
I think, yeah, so some of Larry's work for the rest of his thesis is actually looking at he's done some somewhat similar, more looking at aircraft data, looking at cold air outbreaks in the northern hemisphere. And now the last part of his thesis, he's looked at some of these hemispheric differences. There are significant differences. There's more supercooled liquid water at the top of Southern Ocean clouds, probably associated with different aerosol contributions, simply because in the Southern Ocean there's no land influence, whereas if you go to the north, and the ocean characteristics are quite different as well. In the deep Southern Ocean, you've got this very strong circumpolar currents. You actually see quite a distinct front, which shows up in some of the meteorology as well. There's semi-permanent front around 55, 60 degrees south. So there's very significant differences. And if you think of the Arctic, you've got ocean surrounded by land, the Arctic Ocean surrounded by land, and the Southern Hemisphere, it's the inverse. You've got this Antarctic continent surrounded by ocean. So there are significant differences.
Great. Any other pressing questions? If not, then let's thank Peter one more time.